A very good morning, my dear students. Let's continue the chapter called Alternating Current. In this alternating current, right now, the topic of our discussion is LC oscillations. What is that? LC oscillations. What exactly the LC oscillations? I'll start discussing with you now. Carefully see. There is a capacitor and there is an inductor. There is a capacitor and inductor. So there is no battery or cell is connected in the circuit. Remember, so this is the capacitor and this is the inductor. Capacitor will have positive plate and a negative plate. When this capacitor is fully charged, okay, when this capacitor is fully charged, the simple concept of when this capacitor is fully charged, what happens? And there is a flow of current takes place from here. Okay, when it is fully charged, because when it is fully charged, the work of the capacitor to store the charges. Once it is fully charged, as there is no battery or cell is connected in the circuit, and this capacitor will act as a source for the circuit, right? Or source of current for the circuit. So now this current is passing from the capacitor. That means there is a discharge is taking place in this case. Okay, so that indicates, so there is a discharge is taking place from here. So when there is a discharge is taking place from here, slowly, so this current will be passing through the inductor, and the amount of current passing through the inductor will be increases. So here initially there is an electrical energy. When current passing through this inductor is increased, so that amount of energy will be stored in the inductor is a magnetic energy, my dear students, right? So the electrical energy will be slowly converting into magnetic energy once the capacitor becomes chargeless. Maximum magnetic energy will be stored in this inductor. Now this inductor will behave a source of current in the circuit, and it starts giving the current here. When it starts giving the current, and it will charge the capacitor now. Again, capacitor will become fully charged. It will become the source of the current in the circuit, and the current it will start flowing through the circuit. That means again discharging takes place. So that discharge will improve and increase the magnetic energy stored in the inductor. It goes like that. See, so what is happening in LC oscillations here is, so electrical energy will be converting into the form of a magnetic energy, and magnetic energy will also be converting into the form of electrical energy. So this kind of cycle is taking place here. Electrical energy to the magnetic energy to the electrical energy. So this cycle is taking place in this LC oscillation. Okay, so what exactly meant by the LC oscillation, I'll tell you. And before moving to that, when the capacitor is fully charged, listen, when the capacitor is fully charged, there is an electrical energy stored in it that is called Q square by 2C. What is that? Q square by 2C. So this is when capacitor is fully charged, my dear students. So when inductor is fully magnetized, so this is the energy stored, magnetic energy stored in this inductor is U suffix V is equal to half Li squared. Any confusion here? So these are the equations you might have discussed, you might have learned in the lower classes. Lower classes means the last sessions. Okay. Now, let's begin the topic. What exactly the LC oscillations I'm going to write here? See, when when a capacitor is discharged, when a capacitor is discharged through an inductor. Okay, when a capacitor is discharged through an inductor, electrical energy and magnetic energy oscillates according to simple harmonic motion with a constant frequency and amplitude. That's it. That's called LC oscillation. Simple, right? So what is LC oscillation here? When a fully charged capacitor is discharged through an inductor. See, the capacitance and the capacitor is this one. The charge on the capacitor is discharging through what? Through the inductor. Electrical energy and magnetic energy oscillate. The energy is oscillating. So this oscillates according to simple harmonic motion with a constant frequency and amplitude. So that's called LC oscillation. All right. So that is LC oscillation. Now let's begin the show here. So carefully observe the potential across this and the potential across this according to the Kirchhoff's rule. What I can write here is a minus L into di by dt, right, plus q by c is equal to c. Here q is charge on the capacitor at any instant, right, or at an instant. Let's take it is q. At an instant it is q. Now at an instant of time t, so charge is q, small q. Now at the same instant, and you know I is equal to minus dq by dt, yes or no? Because the charge is decreasing, so that is what this negative sign indicates. So you keep it here. So what it will become? So it will become L into d square q by dt square plus q by c is equal to 0. And what I can also write from here, so this L, both this term and this time you divide with the L. So this will be a d square q by a dt square plus q by LC is equal to 0. So this is the differential equation. Okay. So this is the differential equation which is a simple harmonic motion, which is representing the simple harmonic. And this equation you can also relate with this equation of simple harmonic motion. So d square x by dt square is equal to plus omega square x is equal to 0. So when you compare these two equations, you can see here, so here omega square, here 1 by LC, yes or no? Here oscillating, see the position of the particle is changing. So but here charge with respect to time, the charge amount is changing. Here the charge is oscillating, here the particle is oscillating. Here the particle in the sense mass. Mass is oscillating here, here the charge is oscillating here, right? Both are making simple harmonic motion. Right? So from here, what I can write, omega square is equal to 1 by LC. So this omega is equal to 1 by root LC. So this I can also write it as 2 pi into frequency is equal to 1 by root LC, and it is similar to the concept called resonance frequency, my dear students. Okay, so what is the resonance frequency formula? This one, right? F is equal to 1 by 2 pi into square root L by C. That's the resonance frequency. Okay. Now All right. So what we have concluded is this is the oscillating charge will make a simple harmonic motion. So this is analogous to the mechanical energy, a simple harmonic motion equation. So there are solutions for this. From the solutions of this differential equation, you can find the maximum value of the current is equal to omega naught into the maximum charge. Okay, so remember, so maximum current, this is the, remember, from the experiments only, from the solution of this differential equation, the maximum current you get it as omega naught into Q maximum. What is omega naught? This one only. All right, no confusions. So this you remember. Let's continue here. So now we need to move the energy oscillations and how the energy oscillations takes place. So let's see how the energy oscillations takes place. I'll draw here. Carefully see. The first case, what happens? First case, this is the capacitor. This is the inductor. First case, what happens? This capacitor is fully charged. When the capacitor is fully charged, it will have electrical energy with it, which is Q square by 2C, and there is no magnetic energy associated with it, right? This is the first one. And the second case, what happens? Let us see. Second case, simple. Let it be. Second case, what happens here? So as the fully charged capacitor will start discharging, so here there is only two charges are left, you can see here. So when the current is passing through this, and some amount of magnetic field is associated with it. Some amount of magnetic field is associated. So in this case, electrical energy associated with this is not equal to zero. And the magnetic energy associated with this is also not equal to zero. Okay. And the third case, what happens? Third case. What happened to third case here? Third case, capacitor is fully discharged. Electrical energy associated with this is zero. And the magnetic energy associated with this is maximum. All right. So what is the magnetic energy associated with this is maximum half Li square. Okay. And one more. So here, so when it is reaching to the maximum value, what happens? I have told you clearly, slowly it will discharge now. So this will become the source for the electric current in the circuit, and the current will be started flowing in this way, and slowly, so this amount of magnetic field produced by this inductor will reduce, and slowly there is a positive plate and negative plate appear here. So here also electrical energy associated with this is not equal to zero. Magnetic energy associated with this is not equal to zero. Okay. Now, oh no. So here what happens, see, the magnetic energy associated with becomes zero and capacitor gets fully charged, but the polarity is different than earlier, you can see. So first what happens initially electrical energy is max q square by 2c, and now electrical energy is q square by 2c. Initially a magnetic energy associated with inductor is zero. Now the magnetic energy associated with this inductor is zero, and this is what takes place in a time period of t by 2. In half of the cycle it takes place. How do you know that it is half of the cycle? In half of the cycle, because the polarities are changed here, see. So now the left side plate is positive. After half cycle, right side plate is positive, and for another half cycle, so the same thing will repeat. That means for a time period t, the same one complete cycle will be finished, right? For time period t, one complete cycle is finished. So same thing I'll write here. For a time period t, one full cycle will be done. Full cycle will be done. So this is the situation is similar to, this is the situation is analogous to a spring attached to a block and oscillate. Okay, same situation, same situation. So here this is the rigid support. So there is a spring here. Now this is actually the mean position of this mean position. I can say x is equal to 0. From this mean position, I have taken this block to here. This is my first position. At this first position, what happens? Carefully see. At the first position, so it is so simple. The potential energy is equal to half kx square. Yes or no? Potential energy in the spring and kinetic energy is equal to 0 because at the first position. And if I release it at this particular position, so this is my second position. In the second position is, so the body will be trying to move towards the mean position. So in the second position, potential energy is not equal to 0 and kinetic energy is also not equal to 0, my dear students. And the third position is at the maximum height, at the at the mean position. At the mean position, so the particle will be trying to move with maximum velocity. So at the mean position, so the potential energy will become 0 and the kinetic energy is equal to half into m into v square. So that is the maximum velocity. Okay. And the fourth position will be somewhere here. So this is the fourth position. Still the body is trying to move here. So fourth position, so the potential energy is not equal to 0 and the kinetic energy is also not equal to 0. And the fifth position here, my dear students, what is the fifth position? Fifth position, imagine, so the particle is at rest now, right? So finally the particle is at rest. So I can say the potential energy is equal to half kx square once again, and the kinetic energy is equal to 0 because the particle is reaching to the rest. Same thing you see, this is for half cycle. This is for what? Half cycle, because we have started from here, the body is not at reached to the same position. Okay, so you can see potential energy is half kx square. After half cycle also potential energy is half kx square. Kinetic energy is 0. initially, and the kinetic energy is 0 after half cycle. So this is also the time taken is time t by 2. For full cycle, what happens? Full cycle, again you get the same answer here as the initial. Okay, clear. So this is the concept how the energy is converted. See here, initially the potential energy is half kx square, it is maximum, and finally it is slowly, so the potential energy is decreasing. See here, so potential energy is half kx square, so after some time kinetic energy is half mv square. Okay, so kinetic energy is 0 initially, after some time potential energy is 0. So as you can see, the potential energy values are decreasing, and the kinetic energy values are increasing, right? So this complete concept is depending on law of conservation of energy, my dear students. The complete concept is depending on what? Law of conservation of energy, right? So this is concept called LC oscillation. See how the energy is oscillating. And let's come back to this diagram. How the energy is oscillating, you can see here electrical energy, here electrical energy and magnetic energy both are here, and here it is magnetic energy. After 1, 2, 3, right? Just after this diagram, and after this what happened? Complete electrical energy is getting converted into mechanical energy. Okay, clear? So this is the concept how the energy is oscillating in LC oscillation. Clear? So remember the formula, this one. So maximum current is equal to omega naught into maximum charge of the initial capacitor. Okay, so let's solve few numericals, my dear students, so that you will be confident on some areas. Clear? So let us see. So this is the first example. First example, it's not only based on LC oscillations, and we are solving some other questions even, right? So given alternating circuit where voltage is given as 100 sine 100 t, so that is voltage, and the current values are given 100 sine 100 t plus pi by 3 milliampere. So now the question is, what is the power dissipated in the circuit? Right? What is the question? Power dissipated in the circuit. This is power dissipated in the circuit. So we have the formula in the power dissipated in the circuit concept, right? So here, if you carefully see, so there is a V and I. I is leading. I is leading. So power dissipated, there is a phase difference also. You can find the power dissipated is equal to ERMS into IRMS into cos phi. Okay, because phi is also there. So it is so simple. ERMS 100 by root 2, IRMS 100 by this is root 2, and this is cos pi by 3, cos 60. Cos 60 is 1 by 2, right? So this I can write, this is 100 into 100 divided by 2 into 2, right? So this is 250s, and this is 250s. So I can say it is 2500. And interesting thing is here IRMS, right? IRMS is I naught by root 2. So it is 100 by root 2 given in milliamperes. So this we must add 10 raised to minus 3 watt. Okay, So now 2500 into 10 raised to minus 3. So this you can write 2.5 watt. That's it. In this way you can solve the question. Let's see another question. Another question is a transistor oscillator, right? Let me write the question. A transistor oscillator using a resonant circuit with an inductor and capacitor C in series produce of frequency F. Okay, if L is doubled, okay, and C is changed to 4C, then the frequency will be, that's a question. So simple. A transistor oscillator using a resonant circuit, right? Resonant circuit means, for writing the solution, let me take that. So resonance, F is equal to 1 by 2 pi root LC. From here what I can write, F square is directly proportional to 1 by LC. So from here what I can write, so F1 by F2 whole square is equal to L2 by L1 into C2 by C1. So this is F1 by F2 whole square is equal to L2. So here L is doubled. So L2 is 2L. Initial value is L into C2. C is changed to 4C. So 4C is the final value. Initial value is C. So L cancel and C cancel. So F1 square by F2 square is equal to 8. So from here what I can write, F2 square is equal to F2 square is equal to F1 square by 8. So this F2 is equal to F1 by root 8. So root 8 I can also write it as 2 root 2. Okay. So that's it. So this is the given and this is the answer required. Let's have a look at the another question. Given if power factor is 1 by 2 in series LR circuit, okay, and given R is equal to 100 ohm, we need to find then L is. So they have given F is equal to 50 hertz, my dear students. All right. So let's see. Power factor is 1 by 2. What is power factor? Cos phi is equal to 1 by 2, which is equal to R by Z from the impedance triangle. Okay. So from here I can say your Z value is equal to 2 times R. So 2 times R is 2 into 100. It's 200 ohm. Simple. Z you have, R also you have. So then L, finding L is very simple. Okay. So Z is there and R is also there. Let's start. So we have Z is equal to square root R square plus XL square, because XL minus XC whole square. XC is not there. So because it is only LR circuit is given. So Z is 200, which is equal to square root. So this is 100 square plus XL square. Just apply square root both sides. Apply square on both sides. 200 square minus 100 square is equal to XL square. So this is A square minus B square formula. A plus B into A minus B, which is equal to XL whole square. So this I can write it as 3 into 100 into 100. So if you apply square root both sides, it will be root 3 into 10 into 10, it is 100. So this is XL. Okay, this is XL. Now, one more. What is XL? 2 pi into F into L. So which is equal to root 3 into 100. So we have the frequency 2 into pi into frequency is 50 they gave. You can see here frequency is 50 they gave. So which is into L is equal to root 3 into 100. So now 2 into 50 is 100 and 100 cancel. And your L value is root 3 by pi. Okay. So L is what? Inductance. It is Henry, root 3 by pi Henry. So like these questions will be asked. Let's move on to the next question. One more, last question for the session. Let's make it. So look at this question here. So there is a huge circuit is given. There is a resistance here, inductance is here, capacitor is also here. Alternating source is connected to this. And here they mentioned 50 volt is applied voltage for the complete circuit. There is an ammeter is placed here. Ammeter is placed. And resistance of this is given as 10 ohm. And here potential difference across this inductor, it is given as 60 volt, and the potential across this capacitor is given as 100 volt. And you can say this is capacitive dominance. Okay, so now let's begin the show. Question is, what is the reading of the ammeter? What is the question? Find the reading of the ammeter. So simple. So the ammeter is located here. Ammeter is located here. All right. Now, reading of the ammeter means we need to find I, right? So I is equal to E by Z. Okay. So what is Z? So that's impedance. What is that? So that is impedance. And before that, you know this E. So what is the E sub? This 50 volt, that is the RMS voltage of the circuit E. And one more thing, here itself, let us find that E. So E is equal to square root of VR square plus VC minus VL whole square. Here, this is 50. 50 is equal to square root VR square. So that we don't know. Plus VC minus VL. So VC is 100 and this is 60. So which is 40 square. Now, so this both sides, if you apply square root, you get 50 square minus 40 square is equal to VR square. So it is 90 into 10, which is VR square. So from here, so VR, you get it as, so it's 30 volt. Okay. So what is the potential across this is 30 volt. Now current you can find out. So I is equal to V by R. So where I is equal to V is 30 by R is 10. So what is the answer? So 3 ampere. Okay. So like this, you can solve the question. All the very best for your assignment. See you soon in the next class, my dear students. Good luck.